In this video, we're going to look at Turing machines as problem solvers. In other words, we're going to look at problems rather than languages and ask how Turing machines can be used to solve problems. Up to now, we've been talking about how Turing machines can be used to decide or recognize languages. But we also want to be able to use Turing machines to solve arbitrary problems. And we can do this because any problem can be expressed as a language. In other words, we can turn any problem into a language such that any instance of the problem is a particular string, and that string is either in the language or not. Okay, so it might help to look at a particular example. We can imagine the problem of whether a graph is connected or not. Okay, that's the problem. What's an instance of the problem? Well, that's when we have a particular graph and we're asking, is this graph connected or not connected? So the problem of whether graphs are connected or not can be turned into a language with a corresponding Turing machine. And the Turing machine will, in this case, decide that language because that's a decidable problem. An instance of the problem is a particular graph, and we're asking, is this particular graph connected or not? And we're going to encode the problem, or the instance of the problem, into a string in such a way that if the string is in the language, the answer to the question of whether the graph is connected or not is yes. And if the string is not in the language, then the answer is no. So do you see how we can use languages to describe problems? Every instance of the problem is encoded into a string in such a way that if the answer to the question is yes, the string is in the language, and if the answer to the question is no, the string is not in the language. Let's take a look at this example in a little bit more detail. First of all, we're going to be talking about undirected graphs, and we're going to ask whether a graph is connected. So here's a graph with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nodes. And it's not connected because there are two separate components and there are some nodes that are not reachable from other nodes. For example, this node is not reachable from that node. So we're going to encode this problem into a language. And here's the language. We'll call the language A. And it's the set of strings such that those strings represent a connected graph. Okay, what's going on here? First of all, these angle brackets are being used to say that this is a representation of a graph. This is a representation of the graph. It's a graphical pictorial representation, and it's not appropriate as an input for a Turing machine. In order to input it into a Turing machine, we're going to have to turn this instance of the problem into a string. We're going to have to represent this graph somehow. We might number the nodes, and we might number the edges, and we might have a list of edges and a list of nodes and so on. But we have to figure out a way to represent graphs as strings. And then what we're saying is the language consists of all those strings that are representations of graphs, and furthermore, that are representations of graphs that are connected. And what we want then is a Turing machine that can decide this language. This is a decidable problem, so this is possible. We can find a Turing machine to decide this language. And that Turing machine will accept when the input is the representation of a connected graph. And it will reject when the input is the representation of a graph that is not connected, or it'll also reject if you give it a representation that's not valid. In other words, you give it a string that doesn't make sense. It's just not a graph at all. Okay? Well, this problem is decidable, so there exists a Turing machine that will never loop and always answer correctly. Now, we might have a bad Turing machine that loops sometimes, but we need to get rid of that Turing machine and find a better one. So in this particular problem, we don't have the problem of looping. We can find a Turing machine that will not loop. One key aspect of programming is figuring out how to represent data or knowledge or information. How do we represent the graph? Well, it's easy to represent it with a picture, and it's very intuitive for humans. But in order to represent this thing in a way that a computer can process or a Turing machine can process, we have to turn it into some sort of a string with symbols. And in the end, if we want to represent it inside of a real practical computer, we turn it into zeros and ones, or even into voltage levels. But here's how we're going to represent a graph. We're going to number each node, and we're going to start, and we're going to use some parentheses and commas as well. So our alphabet is going to consist of digits as well as a comma and open and close parentheses. And our representation of a graph will consist of a list of nodes, and these will be the names of the nodes. So we're going to give each node a name that is a number. So we have 4 nodes in this example. So we'll use parentheses to separate the node list from the edge list. So here is a list of the edges. And in this graph we've got 4 edges, from 1 to 2, from 2 to 3, 1 to 3, and 1 to 4. And so we list each edge as a pair with comma separated numbers enclosed in parentheses. And so this graph can then be turned into a string using these symbols. And the string looks something like this. I should probably stop here and talk a little bit about how we represent numbers. There are a number of different ways to represent numbers. The way we normally use is with decimal. And we can represent our nodes with decimal numbers. In that case, this would work just fine with our graph problem. So our alphabet would contain digits 0 through 9, and if we wanted to make larger numbers, we would just have a string of digits. And so here's a representation for node 439. In other situations, it makes more sense to represent numbers with binary values. So here we need fewer symbols in our alphabet, and we can represent numbers. It may take a few more cells on the tape, but we can still represent every number this way. We can also represent numbers in unary. Unary is the simplest number system where we have just a mark for every item. So we represent the number 8 with 8 ones. This is not a very efficient way to represent numbers. As the numbers get larger, the representation gets equally large. But how we represent numbers is really no more than a programming detail. We can process these things with algorithms, and we can implement these algorithms on Turing machines. Remember the Church-Turing thesis, which is that by algorithm we mean nothing more than a Turing machine. If something can be executed with a Turing machine, then it is an algorithm. And by definition, an algorithm is anything that can be done with a Turing machine. We can express our algorithms at different levels of detail. We might have a high-level specification, and we might use either pseudocode, or we might express our algorithm in some programming language. We might have a more detailed description of our algorithm. We can talk about the implementation level specification, and at this level we're adding in information about what the tape looks like, how the data is represented. Okay, in our graph connection problem, we're talking about using symbols, what symbols we use, and how they're laid out on the tape. And in describing the algorithm, we might talk about the motion of the tape head. We might say things like move the tape head all the way over to this mark, or move back to a comma. There's still a lot of detail, but at the same time it's still abstract to some extent. We don't actually have states and transitions. At the lowest level, we can specify the algorithm as a Turing machine, complete with a list of all the states, the alphabets, the transition function. This is a fully detailed specification of the algorithm, and for anything but the simplest algorithms, it's probably somewhat incomprehensible as well. So once we're comfortable with the basic ideas of Turing machines and how to specify the details, we can start to give more and more abstract algorithms. Now, as long as you feel that you can program anything in a Turing machine and that any algorithm can be implemented on a Turing machine, then you can start to talk about algorithms and deal with higher level specifications of the algorithm. We understand that we can build any algorithm with a Turing machine, and we could specify the actual Turing machine whenever we had to. So as we move on, we'll talk not about specific Turing machines, but about algorithms, with the understanding that an algorithm and a Turing machine are the same thing. Okay, an algorithm and a Turing machine are the same thing. That's the Church-Turing thesis. So now let's move on and look at the algorithm for this problem that we're talking about. So the problem is to determine whether a particular graph is connected. The first problem is to determine whether the representation is a legitimate representation of a graph. If it's not a legitimate representation of a graph, then we have to reject right off the bat. But moving on, after we've verified that it is a representation of a graph, we can talk about how to determine whether it's connected. And so here's an example of an algorithm. You should be familiar with this, or this shouldn't be too difficult to understand, particularly if you've made it through an algorithms class. Here's the idea. We select a node and mark it, and then we have a repeat loop. And we repeat until no more nodes can be marked. So what do? For each node, if it's unmarked, then we look, is there an edge from a node that's already been marked to that node? And then if so, we mark that node. Okay, so it's a marking algorithm. We're going to start by marking one node, and then if a node is connected to a node that's already marked, we'll mark it. And we keep doing this until we can't mark any more nodes, until there are no more nodes to be marked. And then we run through our nodes, and for each one of them, we ask, has it been marked or not? And if we find a node that has never been marked, then we can say that it wasn't reachable from the node we started at, and we can reject. Otherwise, if all nodes are marked, then we accept, and we say, yes, this is a connected graph. Reject is a no answer to the question, accept is a yes answer to the question. So the next step in building a Turing machine for a given algorithm is to go down one level in the hierarchy of specificity and go to a more implementation level description of the algorithm. And so here we're describing tape movement a little bit more, and this version of the algorithm is much more detailed. We have things that say, like, check that the input describes a valid graph, which means we have to check the node list. So we have to scan an open parenthesis, and it must be followed by some digits, followed by commas, and so on. And then we check that all the nodes are different. Make sure that no node is repeated in the node list, because that would cause us problems. And then we have to check the edge list, making sure it's pairs of numbers, and then each number is one of the nodes that was in the node list, and so on. And then we get to the actual algorithm. It says mark the first node, so that means place a dot under the first node in the node list, under the first digit of the first node in the node list, and then scan the node list to find a node that's not marked. And it goes on and on like this with lots and lots of detail. This is a fairly complex algorithm, and turning it into a Turing machine is going to take some time. But I think it's pretty obvious that an algorithm like this, or any algorithm that you're used to seeing as a programmer can be turned into a Turing machine. That's the Church-Turing thesis, that a Turing machine and an algorithm, these are the same things.